Okay, this is 5.2, growth and decay, rational exponents. And, it's pretty simple. It's everything we did in 5.1, except the only difference is today our exponents will not be integers, they will be rational numbers. So we're going to learn to talk about how a rational exponent represents a power and a root. So the objective will be to define and apply rational exponents. And let's start with what we began with in 5.1. Yeah, that's right, the hamburger. The cost of hamburgers has been increasing by 9% per year. That implies each year the cost is, well, this is a growth rate, and a growth factor would be 1 plus that growth rate, which would be 1.09. 1.09 times the cost of the previous year. That's 1 plus 9% increase. So if the cost this year is $4, what is the projected cost 1/2 year from now? The 1/2 is the new stuff here. That's a rational exponent. So let's set up our growth model. So C in terms of T will equal our initial cost, which is $4, times our growth factor, which is 1.09 to the T. And now all that remains is we put an input of 1/2 for T. So C of 1/2 will equal 4 times the growth factor, 1.09 to the 1/2 power. And again, you just carefully put that into your calculator. Let me get out my calculator here. And if you have a newer calculator, that 1/2 will go into superscript altogether. And if you have an older calculator, you use that caret and 1/2 in parentheses. So know your calculator, please. Let me clear this out. So I've got 4 parenthesis 1.09, close my parenthesis, to the, and then I've got my 1 divided by 2, 1/2 power. I have a newer calculator, so I put it in exactly the way I see it. And I'm getting 4.176 ... And I probably want to round that to the nearest penny. Would that be $4.18? There you go. Okay, now, remember what I mentioned right at the beginning. This is a rational exponent right here. And a rational exponent gives me both a power, 1, and a root. And that's a square root, root 2 right there. So again, what does b to the 1/2 mean? Well, if I have a rational exponent of 1/2, that's nothing more than a square root. The 2 root of b to the first. Square root of what? B to the first, or b. And that's it. You'll see that a lot. Many times you'll go from a square root to a rational exponent, and other times you'll go from a rational exponent to a square root. Okay, now this is where it really comes in handy. All right, this is b to the 3/2. All right, so I see this as a power of 3 and a root of 2, and the order doesn't matter. So I could do the root first, and that would be a b to the 1/2 or a square root of b to the 1/2, and then the power to the 3rd. And now, again, remember how I said b to the 1/2 is square root of b? So I could put this in like this. The square root of b to the 3rd power. And there you go. Now, I could also write this in another form. Order matters here. Or no, I should say order doesn't matter here. Now, the first time we did the root first, let's do the power first. B to the 3rd. And then take that to the 1/2. And what does that come out to be? Well, a 1/2 exponent is a square root, so that's the square root of b to the 3rd. There you have it. Isn't that cool? So both of these answers in red there or in blue there are appropriate. They mean exactly the same thing. Okay, so let's go totally general here. And again, do we want to do the root first? How about the q root of b? And then we still have not accounted for that power to the p power. So we did the root first, the q root of b, and then to the p power. Or you could have done the power first. So b to the p, and then take the q root of all of that. These are, again, the same thing. I don't know, I think it's a little cleaner over here on the right, but again, it doesn't matter. So let's go to work then. What is this number? What is 16 to the 1/4? Well, I see a fourth root of 16 to the first power, or just the fourth root of 16. So what number can I multiply by itself 4 times to get 16? Isn't that 2 times 2 times 2 times 2? So the fourth root of 16 is 2. Now, what if they had given you this, 16 to the negative 1/4? Well, if you understand your negative exponents here, you already see the answer to this would be 16 to the 1/4, but we've got to bring that down to our divisor, so that's going to be a 1/2. But let's do this showing every step. Okay, so what do we want to do here? Do we want to get rid of this negative exponent first? Looks like that's what I'm going to go ahead and do. So I need a fraction bar. And if I'm going to move this down to a denominator to make that negative exponent a positive exponent, that would leave a factor of 1 in my numerator. And then in my divisor, I have 16 to the 1/4. And I wrote 16 to the 1/4 as the fourth root of 16. Now I have one more step. Let's simplify this. Well, I have my 1 over, and again, what's the fourth root of 16? 2. And isn't that what we said this would have to be before we even began that problem right there? How about 8 to the 2/3? And this is a great opportunity for me to give you my general rule. Okay, and this works for me. I look at the root first. This is a cube root right here. And if I apply the root and I get a whole number, I'm going to do the root before the power every time. So this one, I look at this root 3, and what's the cube root of 8? Isn't that 2? So I'm going to apply that first. So the cube root of 8 is 2, but then I apply the power squared, and that equals 4. Now you could have done the power first and got 64, and then do the cube root of 64. Guess what you'd still get? The 4. It doesn't matter. I like to use the root first when I can because I'm dealing with smaller numbers. All right, now what's 8 to the negative 2/3 again? I hope you can tell me right now that this is 1/4. But again, let's show every step. Now this time, because this root will give me a whole number, I'm going to do that before I move things down. So I'm picturing the cube root of 8 is 2. And that's now to the negative 2 power. And now let's get rid of the negative exponent. So if I move this down, that will leave me a factor of 1 up top, and downstairs here I have a 2 squared, and I'm going to write that as 4. Okay, suppose a car presently worth $8,200, something like this right here, all right, depreciates 20% per year. That was my son when we bought a new truck many years ago, and the first thing he said was, I wanted a blue truck. Unbelievable. All right, anyway, let's set up our growth model and then put in our input of 2 years and 3 months. So the growth model, what is that truck worth today? $8,200. Hopefully in this picture it was worth a little more than that, but let's call that $8,200 today. And now I'm depreciating by 20%. That means my growth rate is negative, what, 0.2? So I'm thinking my growth factor would be 1 plus negative 0.2, which is 0.80. And there's my growth factor right there to the T. Now, let's put it in our input. And again, the title is Rational Exponents, but isn't 2 years and 3 months 2.25? I'm going to use that as a decimal. You could write it as a fraction if you want, but this is probably a lot easier because we're going to use calculator. So let's go C of 2.25. Let's go ahead and punch that out on our calculators right now. Please punch this out with me. So I have 8,200 times my growth rate of 0.8 to the power of 2.25. And what do I get? Oh man, that truck went down in value very quickly in 2 years and 3 months. That truck is now only worth approximately $4,963. Wow, that's kind of depressing right there. Okay, well, let's keep going. So now, we're going to solve some exponential equations. Now, later on when we start using logarithms, we're going to use natural logs to undo an exponential. But, you know, if you can easily get the same base on both sides of an exponential equation, this method is probably easier. And the left-hand side is base 2, the right-hand side is base 8, but we can write 8 as a base 2 number. So that's what we're going to do. So we're going to get common bases and then use the laws of exponents. So on the left I still have 2 to the x, but do you guys agree that 8 is 2 to the third? And if I brought that up, that would have to be 2 to the negative 3. Does that make sense? And now, here's your laws of exponents right here. And look at number 3. B to the x equals b to the y if and only if x equals y. Well, 2 to the x equals 2 to the negative 3 if and only if x equals negative 3. So that is how we solve exponential equations when we can get a common base on both sides. All right, now this looks a little more complicated, but the same thing, because 9 and 27, guess what? Those are both base 3 numbers. So I'm going to think of the 9 as 3 squared, and I'm going to think of this 27 underneath the radical as 3 to the third. But then I have to apply my radical, which is a 1/2 power. Now, let's clean both of these up and we'll have a clean base 3 on both sides. So this is power of a power on both of them. Laws of exponents, and here's number 7, power of a power. B to the x to the y is b to the x times y power. So if I go 3 to the second to the x plus 1, I multiply those exponents. So that's going to be 2 times x plus 2 times 1, or 2x plus 2. Oh, look at that. And 3 times 1/2 is 3/2. And then we're to number 3 again. B to the x equals b to the y if and only if x equals y. So this implies 2x plus 2 would have to equal 3/2. And now solve the simple algebraic equation. Let's subtract 2 from both sides. So 2x equals 3/2 minus 2 would be negative 1/2. And then divide both sides by 2 to get x equals negative 1/4. All right, so now we're solving a power equation, all right? Which means, again, all we're going to do first is, this is 2 steps. We have to undo this multiplication by 4, so let's divide both sides by 4. 4x to the 3/2 divided by 4 would be x to the 3/2. 32 divided by 4 would be 8. And now, how do we undo a rational exponent? We use our power of a power. Our laws of exponents again. All right, number 7. B to the x to the y is b to the xy. So if I want to undo an exponent of 3 over 2, I take the entire expression to the reciprocal of 3 over 2, which should be 2 over 3. And I do that to both sides. Now, on the left, x to the 3/2 to the 2/3 is x to the first power. 3/2 times 2/3 is 1, x. And 8 to the 2/3, let's do the root first. What's the cube root of 8? It's 2. Square that 2. So what does x equal? X equals 4. Huh, these are fun. All right, same type of problem right here. This time, let's add 2 to both sides. So x minus 1 quantity to the negative 1/4 equals 2. And now, let's get rid of this rational exponent with a power of a power. And again, boy, we use this a lot. So what is the reciprocal of negative 1 over 4? That'd be negative 4. And I have to do that on the right too. And what do we have here? Well, x minus 1 to the negative 1/4 to the negative 4. Negative 1/4 times negative 4 is 1, so that's just x minus 1. And 2 to the negative 4 is 1 over 2 to the 4th. And what's 2 to the 4th? 2 times 2 times 2 times 2. That's a 16. So let's add 1 to both sides and we are done. So x equals 1 plus 1/16 would be 17/16. Okay, and some people want to write that as 1 1/16. You can. Typically in advanced mathematics, we like to use improper fractions because if we're in the middle of the problem, it's a lot easier to do operations with an improper fraction than it is for a mixed number. Okay, here's our last problem right here. A house bought 5 years ago for $100,000 just sold for $135,000. This looks like a great opportunity for a growth model and a little exponential equation right here. So how much did the house cost me and how many years was that ago? Well, let's start with this time. 5 years. And I'm thinking of $100,000 as my initial cost of my house. So I'm going to make my T a 5. And then this is 100,000, which I'm going to write as 100. Because guess what this has to equal? 135,000. So on the left, I'll just put 135. Now, if you want to put 100,000 and 135,000 there, you can. We'll get the same thing. But now, a house bought 5 years ago, T equals 5, for $100,000, A sub 0 is 100, was just sold for $135,000. To the nearest tenth of a percent, what was the annual growth rate? So our growth factor would be 1 plus the growth rate. All right. And now we solve for that growth rate, R. So first thing we better do is divide both sides by 100. 135 divided by 100 is 1.35. And then on the right, we have 1 plus R to the 5th. And now, again, how do we get rid of that 5th power? We do both sides to the 1/5 power. Power of a power again. Right down here, number 7. Man, we use that a lot. So let's go 1.35 to the 1/5. And then if I go the quantity 1 plus R to the 5th to the 1/5, that's just going to leave me 1 plus R. Now, what does R equal? Let's go 1.35 to the 1/5 minus that 1 over there. And now let's punch that out carefully and make sure we round appropriately. So I'll punch it out with you. 1.35 to the 1/5 power minus 1. I always check, is everything in okay? Yeah, it is. And I'm getting 0.061858 ... Now I need the nearest tenth, so how about if I start now with 0.0619. Okay, now tenth of a percent. So I've got to move this decimal 2 places to the right. So 6, and then tenth of a percent. Wouldn't that be 6.2%? So R, my growth rate, is approximately 6.2%. All right, so today I'm giving you some class exercises and some written exercises. All right, 1 through 17, every other odd. 21 through 57, every other odd. Have fun and get a hold of me if you have any questions.